Hi, class. I was getting some questions on how to do the little assignment on the Blackbody spectrum. So I have this set up at my home where I have this mic that I'm going to try to record my screen and also show you some things by talking about it directly. Here on this right hand side, this is the temperature of our black body that we're interested in, okay? We can change the temperature, and you're going to notice, oh, look, this spectrum changes depending on how hot the black body is. Up here is sort of like a representation of the lights, the um, visual depiction of the electromagnetic radiation coming off of the black body due to its temperature. So we'll see at very low temperatures, things look dark. That's because they're very cold. They're not emitting much energy. At very high temperatures, things look kind of blue. That's because blue is a more energetic part of the visual light spectrum. How does this relate to Wien's displacement law? And finding peak wavelengths? Well, I'll show you. And the simulation I think is kind of helpful. Let's set the temperature to 3000 Kelvin, which is about as hot as a light bulb. And you see a very low spectrum. Um, this y axis is energy, not very obvious exactly what's going on here. We have to change the scope of our y axis. Let me zoom in. Let me zoom in. Okay, now we have something that resembles a spectrum. What if I hit graph values and labels? This graph value, it's telling us exactly, you can move this around and we can kind of see where this peak is happening. It looks like about 0.966. Okay, that's awesome. That's where our peak wavelength is. And we have these areas, ultraviolet, visible, infrared. So this peak is in the infrared part of the electromagnetic spectrum, and about 0.966 micrometers or 966 nanometers. Okay, now Wien's displacement law says the peak wavelength of a black body is this constant divided by its temperature. So let's compare the value from the graph to what I might calculate on my calculator using Wien's displacement law. Okay, so let's see, 2898, 2.898, excuse me. To the negative 3, that's divided by 1,000. Okay, then let's divide by 3,000 Kelvin. Oh, and I get 0.000000966. That's actually 966 times 10 to the negative 9, 966 nanometers. So according to this, Wien's displacement law helps us to find the peak wavelength, which we can also see on this interactive simulation. I hope this helps. Do this for the temperature of the sun and the temperature of Sirius A also, um, and do the math also.